Welcome to this demonstration on real vibrations dual channel spectrum analyzer. This system is designed specifically for impact excitation for modal analysis. It is targeted for engineering students as well as experienced engineers to compute the modal properties of structures. One of the features of a system is that it works with a vast range of data acquisition systems. Currently we have a small national instrument 8-channel analog to digital converter module. It's a USB 6009 connected to the system, and we're just using 2 channels at this stage. I have the first channel connected to a modal hammer with a force sensor, and the second channel is connected to small accelerometer, which is mounted on a beam. The system is fairly easy to use. We're connected on a single-ended connection for the 14-bit converter, for the modal hammer to channel 2 and the accelerometer to channel 5, and the timeout is for a trigger, so I'll set it at 15 seconds if it fails to detect the trigger. And then we set up the acquisition. So we set up the trigger condition. It can be falling or rising. We set up a trigger voltage, so I'll put 2 volts. We set a pre-trigger delay of say 50 milliseconds, or make it 20 milliseconds. And we set a sample rate here. Let's go at say 8,000 Hertz, which is very high. This thing can go to 24,000 Hertz. And I wish to record the response for say 6 seconds. I will measure 6 times 8,000, which gives me 6 seconds. The excitation unit will be in newtons. So I shall put the sensitivity of the modal hammer in the system. I will now put the sensitivity of the response accelerometer, which is 0.028 volts per meters per second squared. And we will give beam A a name to the file where the data will be recorded. So I'll press OK, and now we're ready to collect the data. There's a few things I can do. So what with the layout of the screen is we'll have the excitation waveform and the accelerate and the response waveform here on the left, top and bottom, and we'll have the auto spectra of the force, impact force, which I'll select on log axis, and we'll have the auto spectrum I should say, of the response acceleration, and here we'll have the magnitude frequency response function, which in this case will be accelerance, and I will also set that onto a log scale, and we'll have a coherence, and here I will select a semi-log scale, so I'll put the x-axis on log scale to match the FRF. So this is tricky because I shall be using the modal hammer with one hand, so I'll collect the data, and the system will wait for a trigger, and I've now struck the beam, and you can see the response. And at 6 seconds you can see that we've collected a set of data. It's not perfect. You see the 2 waveforms, the impact from the hammer, which is not a perfect impact, but for demonstration purposes that's adequate. And you can also see the response, acceleration. We've picked out 2 modes here. You can see the first and second mode at the beginning. And we have the auto spectra. And of course we have no coherence. And now we can choose to include these measurements in the average, because we're going to do some averaging here. So we might do say 3 to start with. Okay, so now we've calculated the FRF and the coherence, of course, which is 1. So now we're ready to collect another a second set of data striking at the same node on the beam. And I've just struck the beam, and now we're measuring the response. And we have a second set of measurements, so we'll include that in the average. Now we're getting a coherence, and I will collect the third set of data. Waiting for a trigger. I've just struck the beam. We have a decaying response, and there we have it. So I have three measurements, or repeat measurements, and we include in the average. And we can clearly see the FRF. We can, if we wish, rescale the graph to linear scales. We can see the first and second mode. If we could use the zoom facility, we can pick out the first mode and the second mode. Not very clean, but this is what experiments does for you. So this is great for students to actually see exactly what's going on. And the data is stored. One of the great features of this system is that we can now rerun the test by engaging a post-processing. So every single bit of information we have recorded has been stored. And now all we need to do is change the test type to post-processing. So essentially we can rerun the test. And if I do that, and I go to the acquisition, and I can select my beam. And here are my three measurements, beam A, for instance. And this, it loads the setup, the configuration, the way I had it. And now we open the first file. So remember we had 3 repeats, and this is exactly the same data. So this is a great advantage, especially for teaching. I will show you another example we did here on a guitar. So I'll set up a test type for post-processing, and I'll go to acquisition, and we'll select the guitar. Here we have a number of measurements, a repeat measurement, so 1, 2, 3, so we'll do that. So this is response at 8, striking at 1, and we have some repeats here. So we'll open, and this was the settings, or these were the configurations. So we had a model hammer, sensitivity, an accelerometer sensitivity, and so forth. And we'll open the first signal, and you can see the impact is hiding behind here. We can actually zoom in on it, and here's the impact force, and here's the response that was from a guitar, and it's fairly, we picked up quite a few modes here. So now we can edit the system or the data, if you like, to include in the average. And we can open the second one. We can see a nice spectrum here, very nice indeed. We can include that in the average. Open the third, include in the average, and open the fourth, we'll include in the average. I think there were more than that. And we keep opening them until the system detects that, in fact, we took 5 averages there. It says here 5 averages. And we can rescale this spectra. So here we have the spectra on linear scales. Let's have a look at what it looks like on log scale. So we have 2 modes. And the coherence is pretty good over that range. So here, if I wish to isolate the mode and analyze this mode, the first mode in this case, to see if we can obtain a Nyquist plot. You can see the Nyquist plot. So on the left we have on the right to start with, we have the accelerants, which is the data we measured. And on the left we have the mobility, which will give us damping. What we can do here, we can do a circle fit. So the circle fit really extracts the mode, the natural frequency, gives us a much better frequency resolution. And looking at the mobility, it will give us the damping. So here we can basically extract the data from a circle fit. So this is a circle fit on the first mode from an average of 5. There's an average, independent averages of 5 on that guitar. And this here we have not only the mobility, which is, pardon me, we get the estimate of the damping constant, but also we can extract the natural frequency much more accurately. So if we use the cursor, instead of using the actual raw data, which is a yellow circle or the yellow Nyquist plot, we can use information from the fit circle to get the natural frequency, which and here, there you have it. One of the advantages of this system is with some fairly simple treatment of the many FRFs that we can collect in that fashion. Not only we can extract the natural frequencies and the damping of each mode, but we can also generate mode shapes. And this is a demonstration on a tennis racket, which we've done. And here we have 12 nodes, so we know where the nodes were, where the measurements were done. So this is how we do it. We take a photograph and we find the markers. We know where the markers are, and then we tag the nodal points to the correct FRF. And this is well, this looks like a second mode of the guitar. So this technique for two-dimensional objects only is to take a photograph of the objects in the right plane, and then using these nodal points to capture the FRF data, and then tagging the FRF data to the correct nodal point, we can then generate the mode shape animation as you see here. I do hope you enjoyed this short demonstration, and feel free to visit us on our website should you have any queries. Goodbye.